Now that we've introduced the topic of a basis of a vector space, we're going to introduce what it means to be the dimension of a vector space. So if a vector space V has a basis b1 to bn, then any set in V containing more than n vectors must be linearly dependent. We're not going to talk about the proof of this theorem too much, but we will kind of understand why it's true. So let's say that we had another set in V, let's call it S, that consisted of more than n vectors. Let's call them V1 to Vn, and we'll just have one more, Vn plus 1. Now all of these vectors can be written as a linear combination of the basis vectors. C1, B1, C2, B2, all the way to Cn, Bn. And that's because the basis spans the vector space V. So any vector in that vector space can be written as a linear combination of those basis vectors. And although some of the details are missing, the idea is that since we can rewrite all of these vectors Vi as a linear combination of those Bi's, what we can do is use a result from the previous section that if we have too many vectors, we can delete one of the vectors and then create a basis from that point. And since we have too many vectors here, we're able to do this. So going back to just the statement, just know what we have. We have that if we have a basis with n vectors, any set containing more than n vectors is necessarily linearly dependent. We talked last time that a basis is a maximal linearly independent set. And that's what we're going to have in this section as well. So the next theorem says, if a vector space V has a basis of n vectors, then every basis of V must consist of n vectors. So every basis has to have the exact same size. And the proof is a quick little thing here. We're going to consider two bases, B1 with n vectors and B2, and we're going to show that B2 has exactly n vectors. Since B2 is an arbitrary basis, we will show that every basis has exactly n vectors. So from the definition of a basis is a linearly independent spanning set. Because of that, both B1 and B2 are both linearly independent sets. So if B1 has more vectors than B2, then using the theorem above, this means that B1 must be linearly dependent because it has more vectors than a basis. And the same way, we have that if B1 has less vectors than B2, then B2 must be linearly dependent. But that would be a contradiction. So the only thing that we have is that B1 and B2 are the same size. The same number of vectors. So therefore, B2 has exactly n vectors. That means that every basis is the same size. And that's going to talk about what we mean by dimension. So if V is spanned by a finite set, if we're talking about a basis has a finite number of vectors, it's said to be finite dimensional. And the dimension of V, written as dim of V, is the number of vectors in a basis, which we just showed has to be unique to that vector or to that vector space. A couple things to note: that the dimension of the zero vector space, 0, is defined to be just 0. Although there is one vector in that span, that the vector is just a 0 vector, there's something special about that. So we say the dimension of the 0 space, which is just the 0 vector itself, is 0. And if V is not spanned by a finite set, then V is said to be infinite dimensional. And we're not going to talk about infinite dimensional vector spaces in this class. We're going to stick to just finite dimensional vector spaces. So let's look at an example of some vector spaces we've been using in the past few sections. We talk about P3. P3 is the set of all polynomials with degree at most 3. And the standard basis for that vector space is going to be the polynomial 1, t, t squared, and t cubed. Every polynomial we want can be written as a linear combination of those vectors, and that is a linearly independent set. And we showed that in the last section. So because this is a basis, we know that the dimension of P3 has to be 4, as 4 vectors make up the basis. And in general for Pn, which is the set of all polynomials of degree at most n, we have that the dimension of Pn is n plus 1. Another example is the standard basis for r to the n. And we talked about how that's going to be this e1 to en. Ei is the ith column of in. It is known as the standard basis vector, the ith standard basis vector. And in this case, the dimension of Rn is just going to be n for any. So for example, R3, we look at a basis for R3. We have this standard basis vector, which is going to be 1, 0, 0, 0, 1, 0, and 0, 0, 1. And that means that the dimension of R3 is 3. So let's look at a more complicated example now. Let's find a basis and the dimension of the subspace W defined by this matrix here where A, B, C, and D are real numbers. As we've done in the past few sections, what we're going to do is we're going to break up this vector in W, given by a bunch of different parameters A, B, C, and D, into a vector equation. So we can get different vectors and write them as a matrix. So we're going to break this up into all the things multiplied by A plus all the things multiplied by B, C, and D individually. And we get this vector equation here with the linear combination of 4 vectors. And just for the ease, we're going to write this as V1, V2, V3, and V4. So we get this linear combination AV1 plus BV2 plus CV3 plus DV4. And that means that W, this vector space W, can be written as the span of all those vectors. But this does not necessarily mean that the basis are those vectors. So this does not necessarily mean and we talked in the last section that you may have too many vectors in the span. It's not an efficient way of writing that span, and you may be able to delete vectors from that span and still have a basis. So that's the next question we have to ask is, can we delete vectors from that span to get a basis? And the way we're going to do that is to look at the column space of the corresponding coefficient matrix corresponding to those vectors in the vector equation. In this case, we have V1 is the first column of A, and V2 is the second column, and so on and so forth. And if we look at that matrix A, we are saying that W is going to be the column space of that matrix. That's just another way of writing what W is. It's a linear combination of those columns. And if we row reduce this is now going to be in row reduced echelon form. We can look at the pivots of that matrix. And in this case, we have 3 pivots of that matrix. And we have 1 free variable. And we said in the previous section that a basis for the column space of A can be found by looking at the pivot columns of A. So the pivot columns are going to be the first, the second, and the fourth columns. This is the pivot columns. And therefore, those 3 columns in the original matrix A are going to form a basis. So in this case, we have a basis is going to be v1, v2, and v4. We can write v3 as a linear combination of v1, v2, and v4, and that comes from the fact that it is a free variable in the row-reduced echelon form matrix. So because this is going to be a basis for the column space, and it has 3 vectors, then the dimension of the column space, which is the same as the dimension of W, is 3. To review this example slightly, this subspace W is not given in a matrix form at all, but we've seen throughout this course that if we can bring this into a matrix in some way, we have nice, easy ways of determining some important characteristics, in this case, the basis. And what we need is a row-reduced echelon form of that matrix to determine the information. So if we can translate a subspace like this W, which is just going to be a vector in R4, this is a subspace of R4, we can still write it as a 4 by 4 matrix if we think about it as a vector equation first. So now let's look at some dimensions of subspaces of R3. We can think about this geometrically, and that's really what we're going to be doing here. So we have 4 different kinds of subspaces. We have the 0, 1, 2, and 3-dimensional subspaces. We said that the 0-dimensional subspace contains only the 0 vector, and in that case, that is a point in R3. And what point is that? It is the origin in R3. So if we draw our axes, the subspace containing the 0 vector only is just that one point at the origin. The one-dimensional subspaces, that is, we have one vector in the span, or one vector in the basis. We need to have that one vector not be the 0 vector, and in that case, these subspaces are going to be lines through the origin. And again, if we draw a little picture here, we have some line that goes through the origin, and that's going to be a subspace with one vector, a one-dimensional subspace. If we have 2 vectors in the basis, then the span of UV, as long as U and V are not multiples of each other, that means that the basis has 2 vectors, then these subspaces are going to be planes through the origin. So if we draw a little picture here, we have some plane, and it's going to go through the origin at some point. And then finally, if we have a 3-dimensional subspace, we look at the span of 3 vectors, and those 3 vectors have to be linearly independent. That means that we don't have constant multiples of each other, and we can't write any vector as a linear combination of any other vector. Then the subspace is just R3 itself. We say that this spans R3. So what we have here, and why we call this the dimension, is because when we think about a point, a line, a plane, and then R3 space, that is a 0-dimensional space, a 1-dimensional space, a 2-dimensional space, and a 3-dimensional space. And now we can even say things about how many vectors it takes to describe that space in total. If we think about a line, we only need one vector to describe that line in total. The plane, you need 2 vectors. The whole R3 space, you need 3 vectors. And then the 0-dimensional subspace is kind of unique. You only need one vector, but it's a very special vector, the 0 vector. So now let's talk about just generic subspaces. So let H be a subspace, and we need a finite dimensional vector space V. This is not necessarily true if we have infinite dimensional, but we're not going to talk about that in this class. Then any linearly independent set in H can be expanded, if necessary, to a basis for H. And also H must be finite dimensional, and the dimension of H has to be less than the dimension of V. And that part should make a whole lot of sense here. We have H is a subset of V, so the dimension of H has to be less than or equal to the dimension of V. And what we're saying here is any linearly independent set in H can be expanded. And that's the idea that a basis is a maximal independent set, linearly independent set. So if I have some independent set that can be expanded to a basis, then I will then get a maximal linearly independent set. And let's see how this works with an example. So let's look at V being R3 and H a subset of R3 given by the span of these two vectors, noting that this is a plane in R3, which we just said in the previous page. And we know that the dimension of H is less than or equal to the dimension of R3. That is, the dimension of H is 2, the dimension of R3 is 3. But given just this dimension of these, the spanning set of H, this basis of H, then we can expand that to get a basis for R3. We can use the smaller subspace to build a basis for R3. So what we're going to do is we can expand this basis for H and add the vector 0, 0, 1 to form a basis for R3. And the idea behind that is the first two vectors, the ones in H, span to give you any value in the first two coordinates of that vector. But the third vector has to be 0. So a way that you could describe this set, this is going to be the set of all vectors A, B, and 0, such that A and B are real numbers. And what we're missing is that third coordinate of that vector. So if I could just add something that just takes care of that third coordinate, the 0, 0, 1 vector, then I can get something that spans the entire space R3. We can verify this by showing that this span is linearly independent and spans all of R3. And note that this is not the standard basis vector, but there's lots of different bases that we could have. This is a little bit different, but it still works as a spanning set. So now let's look at this basis theorem. Let V be a p-dimensional vector space with p greater than or equal to 1. So this is not necessarily true for a zero-dimensional vector space, but anything greater than that. Any linearly independent set of exactly p vectors in V is automatically a basis for V. And any set of exactly p vectors that spans V is automatically a basis for V. The idea here is that if we know that a basis has p vectors, then every basis has to have p vectors. And since we know that a basis is a linearly independent spanning set, and we know that a basis is a maximal linearly independent set and a minimal spanning set, then we get this idea that if we have exactly p vectors, all we need to show is that it is either linearly independent or that it's spanning. So let's look at an example of this. Let's show that this basis, or this set, t, 1 minus t, 1 plus t minus t squared, is a basis for P2, the set of all polynomials of degree at most 2. This set has 3 vectors, and we know that the dimension of P2 is 3. So in order to show that this is a basis, we need to show that either B is linearly independent or that it spans P2. We don't need to show both, we just need to show one or the other. And we're going to show the linearly independent case in this example. So that means that we need to show that a linear combination of those vectors when it equals 0 implies that the constants are 0. And there's a trick that we can use when we're talking about polynomials, and that is that we have this linearly independent, linear dependence relation, and this has to be true for all values of t. That is, all real numbers. So what we could do is we could just pick special values of t to create a system of equations of ci. And some special values that might work are values that will get rid of one of the vectors. So for instance, if we let t equals 0, then the linear independence relation gives us c1 times 0 plus c2 times 1 minus 0 plus c3 times 1 plus 0 minus 0 equals 0, gives us c2 plus c3 equals 0. Then we can pick t equals 1. Where does t equals 1 comes from? That comes from that second term in that linear dependence relation. That if I plug in t equals 1, that will get rid of that entire second term. So this will be c1 times 1 plus c2 times 1 minus 1, that's going to go away, and c3, 1 plus 1 minus 1 equals 0, and that will give us c1 plus c3 equals 0. And we learned from the beginning of this class, as well as from algebra, that if you have three unknowns, c1, c2, and c3, we need three equations to solve for those unknowns. So in this case, we're going to have another value of t. Let's pick maybe the easiest thing I can think of. How about negative 1 will be kind of nice. And if I do that, I'm going to get c1 times negative 1 plus c2 times 1 minus negative 1 plus c3 times 1 plus negative 1 minus negative 1 squared equals 0. It's not going to be as nice as the other ones, but we have negative c1 plus 2c2 plus 1c3 equals 0. And we have this system of equations that we can put into an augmented system. We have a negative 1, 2, 1 augmented with the 0 matrix. That's from this first of the equation with t equals negative 1. We have a 0, 1, 1, 0. That's from this t equals 0 equation. And we have a 1, 0, 1 from the c1 plus c3 equals 0. And we can row reduce this matrix to give us a negative 1, not negative 1, sorry, we're going to do row 1 plus row 3 into row 3, and that'll give us a negative 1, 2, 1, 0 here. Second one's going to be left unchanged, and the third row is going to be 0, 2 plus 0 is 2, 1 plus 1 is 2, and then a 0. And then if we do this one more time, we can get negative 1, 2, 1, 0, 0, 1, 1, 0, and we could do a negative 2 row 2 plus row 3 into row 3, giving us a 0, a 0. And I have a little error here, sorry. This C3 should give us a minus C3, which gives us a minus 1 up here. And if I take minus 1 plus 1, I get a 0. And then this will give us a negative 2 here, which is what we need because now we have 3 pivots. So we have no free variables, which means this is linearly independent. So once again, just saying the mistake that I made real quick, the coefficient in front of C3 in this last equation should be a negative 1, and if we change the values in the augmented matrix, we should get 3 pivots in our row-reduced echelon form, or this is just echelon form. So we showed that it is linearly independent, so therefore this has to be a basis for P2 because it has the same size. And now let's talk about the dimensions of some special subspaces we have, the column space of A and the null space of A. And we have some techniques to find basis sets for the column space and null space, and that's going to help us determine the dimension, as we're just looking at the size of the basis sets. So let's look at this example, A, which is a 2 by 4 matrix, and we're going to find the dimension of the column space and the dimension of the null space. So first, let's look at the column space. In order to find a basis, we're going to look at the pivot columns of A. So we're going to row reduce that matrix into reduced echelon form, or row echelon form, and we can see that there are 2 pivots in that matrix. So therefore, our first and third columns are pivot columns in A. And therefore, our basis is going to be those 2 pivot columns, 1, 2, and 3, 7. And that's going to form a basis for the column space, which means that the dimension of the column space will be 2, as there's 2 bases, or 2 vectors in that basis. So for the column space, we reduce, we look at where the pivot columns are, and then we use the original columns in the matrix to form the basis. For the null space, we need to solve the homogeneous equation AX equals 0 by row reducing the corresponding augmented matrix. So when we row reduce the augmented matrix, we have the same row operations as we did for the column space, and we get the same echelon form matrix augmented with the 0 matrix. In this case, we're going to solve this equation. So we're going to look at the 2 equations here. x1 is negative 2x2 minus 4x4. Before we do that, this is in echelon form. We need to actually put this into reduced echelon form, but that's very quick because we can just rewrite it as a 0 in that last spot. This is by doing negative 3 row 2 plus row 1 into row 1. And now we can see where these equations come from. So this is a good reminder that we should be using row reduced echelon form to solve this matrix. The fact that there is a 3 here is an issue if we want to solve the matrix. We have to get rid of it, and we can very quickly in this example. So we have these 2 equations. x1 is negative 2x2 minus 4x4, and x3 is equal to 0. And we have that x2 and x4 are free variables. So if we look at our solution, we have our vector x is going to be equal to x1, x2, x3, x4. And we can write x1 as negative 2x2 minus 4x4. x2 is just going to be equal to x2. And x4 is equal to x4. And x3 is just going to be equal to 0. And this is going to give these 2 vectors are going to span the null space, and they are automatically linearly independent. So therefore, this is going to be a basis. And those 2 vectors give us the basis. Remember that the null space is a subspace of, in this case, R4, and the column space is a subspace of R2, and that's because A was a 2 by 4 matrix. And since there are 2 vectors in my basis, the dimension of the null space is 2, and in general, the dimension of the column space of A is going to be the number of pivot columns of A, and the dimension of the null space of A is going to be the number of free variables of A. And we're going to talk in the next section about how these 2 numbers relate. In fact, that we have the number of pivot columns plus the number of free variables is going to give us the number of columns of that matrix. And that's going to be a very useful fact that we'll talk about in the next section.